Alright. Is there a mouse here? No? No, just go with, alright. So, I'm not a biologist, that's the caveat I have in every presentation. This is not about biology, but it is about something that's pretty important, which is the fundamental units that are making up the river, and how they interact with climate, and basically how it influences stream temperature or river temperature. Okay, so we know this, right? We're in an age where there's mass amounts of data, and nowhere in particular is there more data than the surface of the Earth. So NASA in 2000 introduced a shuttle radar topography mission, and it gave us unprecedented coverage of the Earth's surface. So this is all surface, all right? So 30-meter resolution is the pixel size. So a pixel is essentially, if you take a photograph on your phone and you zoom in on it, you have these little squares, that's a pixel. So in that pixel, you have information for the geospatial stuff. You have X and Y, so you have a position in space, and then you have Z, which would be your elevation. Again, this could be temperature. You could have X and Y, and then you have T would be your temperature. So you have a spatial location for the measurement that you have. Adjacent to this, we have LiDAR, which is light detection and ranging. It's the same thing Yanni's using, but it's not sound, it's light. And we have this for the province of New Brunswick, so rather than 30-meter resolution, now we have 1-meter resolution. And it's 6 points per meter squared, so it's really high density stuff. We also have a National Hydrographic Stream Network for Canada. So basically, you can see the coverage of it there is for the whole country. It's basically a coalition of regional data sets meshed into one. And this is at about 1 kilometer square drainages. So what do I mean by that? I mean that it takes, if you have a depression, there has to be a flow accumulation within that depression of 1 kilometer squared. And that's going to say, all right, this is a stream, roll on with that. So that's about the coverage that you're looking at there. However, with the light detection and ranging, you can go way down. So we can basically derive 3 hectare drainages. So 3 hectare is 1/100th of a kilometer squared. All right. So this is 300ths of a kilometer squared. So we can really increase the stream network density here, and we can start to look at ephemeral flows and different kinds of streams. So I'm going to present a couple of models now, and I won't spend too much time on the models. I'll go through the concepts more than the models. But what we're going to do is we're going to see, can we compare this coarse resolution data to this really fine resolution data? So, and the idea, I suppose, is that the more high resolution your data, the more you should be able to explain the system, right? Kind of makes sense. So we also have thermal infrared imagery that we're using, and again, this is really high resolution stuff. We flew the Keynes in 2008, 53 kilometers of it. We did the North Pole Stream in 2009, the whole thing. So 35 kilometers, starting at the headwaters and down. And this is what your imagery looks like. So here you have an aerial image of an area, and then you have the thermal image, and you can see the seep. So here the cool water is purple and the warm water is yellow. So you can see the seep coming out here that you can't identify in this image. Similarly here, you have a trip coming in here, and we see that this is actually a cold water trip. Right? So it's really powerful stuff about what you can see about the spatial arrangement of the thermal regime of the rivers. We're also going to use a spatial statistical model, and I'm not going to get hung up on this too much because we can talk about this till the cows come home. It's basically based on semi-variograms. So what that means is it's based on Tolber's first law of geography, and that's very simple. The closer you are to something, the more similar you should be, right? So I'm from Ireland. If someone else is from Ireland, they're going to sound more like me than somebody from the Miramichi, right? So we're closer together, so we're going to sound more similar. And that's all that's doing. And it measures this through a semi-variogram, or a torsiogram for rivers. So what we have here is that's your semi-variance or your dissimilarity. Okay, so this would be very similar. This would be dissimilar, right? So you're more dissimilar than an object. And here you have the spatial representation. So the further I go from this point, the more dissimilar I am to it. Does that make sense? All right. That's all it is. It's not more complicated than that. They also use Euclidean distances and stream network distances. So typically, Euclidean distances as the crow flies. So if I have a point in this tributary here, typically before we'd say, all right, we're going to go look at the distance between these 2 points and down to there. But that's kind of bullshit because it's not how the stream works, right? So really what we have is a stream network. So these models actually take into account the stream network rather than as the crow flies. And again, they can take into account asymmetric distances, so it can be upwards and downwards. So these are the bells and whistles. This is the most cutting-edge spatial statistical model we currently have. So with that, our question becomes, can we increase the power of our stream temperature models? And why would we want to do this? Well, for land management, for climate change predictions, like whatever you want to put on there, flow regimes, it's all going to be a component of the stream temperature model. Because stream temperature is a really good tracer of what's going on in a river or a landscape. So we're saying, can we increase the power of the temperature models with high-resolution topographical data? So that's where we're going to compare the satellite course data to the LiDAR data. And then we're going to use this high-resolution thermal data, so that's the TIR stuff. And then we're going to use this cutting-edge stream network spatial statistical model, right? So we're going to basically say, okay, we're going to throw everything we have, and like I'm not being full of crap here. Like New Brunswick has probably the richest data set for topographical features. It's unprecedented. It's incredible. And we also have this thermal infrared imagery, so we've got a nice little data set here. All right. So the first site is the Keynes River. The Keynes River is located in the Maritime Plains. So what that means is that it's relatively flat. So the can't really see it there. The elevation goes from about 188 meters above sea level to about 11. A lot of wetlands up here, as you can see in the upland, and you have incised channels in the very bottom, or excuse me, in the middle of it, due to past glacial processes. This is the bedrock lithology. It's mostly sandstone and fluviatile conglomerates. So sandstone is dependent upon how fractured it is and what's happening through time with weathering. It's going to permit the flow of water through it. All right. So there's going to be water stored in the ground there. And again, our superficial geology, which is incredibly important too. I'm not going to talk about too much about it though. This is typical of what you'd see in a glacial landscape. So moraines, estuaries, kettle gangs, like wetlands, glacial or clay deposits, the works. Our other site is the North Pole Stream. So elevation here is a lot different. It's 730 meters at the highest point, and it goes down to about 265. The bedrock lithology here is different. So here we have granite rock. So that's going to be impermeable, depending upon how fractured it is. So we have two different types of granite here, or felsic intrusions, two different age classes. And then we have this Cambrian Ordovican deposit. So that's sedimentary rock as well. That's an old ocean floor that's been pushed up into the highlands. And this is about 488 million years old. So this would be, again, pretty porous. Water's going to move through it. And then, of course, our superficial geology is similar. It's going to be what you'd expect in a glaciated landscape. So we threw the kitchen sink into this. I'm not going to go through this in too much detail, right? It's just to give you guys an idea. We included metrics for climate, for physical geography, for hydrography, for geology, and then for land use. So we really want to figure out how the landscape composition might be influenced, and climate, of course, is going to influence the temperatures in these rivers. All right, so we'll go straight into it. I'm not going to. So these are the results. Bear with me, all right? So we'll get into the conceptual stuff in a minute. So this is the Keynes model. So this is the course model with the 1 kilometer squared. So with that, when we overlay it on the thermal infrared imagery, we have about 102 observations of temperature, where we have overlapping of incoming tributaries and the main stem. So this here, aspatial, so it's not taking into account that Tolber's first law. It's just a simple multiple linear regression. For R squared here is about, we have 80% of the variability explained. Thing is, climate's not in this at all as a significant variable. Now what happens as we go through and we apply these high-end spatial statistical models, the amount of value that we explain drops. Now somebody might come to me and they might go, well, yeah, the AIC is low here. I don't care about that AIC. That AIC is penalizing because I have one covariate here. And we're losing 60% of the variability explained. So I'm really, okay, what's going on here? The other point is that the same covariates are popping up throughout the model. So the model is obviously pointing towards something, and it's our job to tease out what it is. We have a positive correlation for wetlands, positive correlation for wetlands. So basically this is saying that the more and these are upland wetlands, so the more wetlands you have in this upland area, the warmer your stream temperature is going to be. That's what the model is saying. Then we have valley wall slope. So that's just basically the pitch in the valley wall, like how steep is the valley wall. That's got a negative weighting to it. So the higher the valley wall slope, or the greater the pitch, the colder your stream temperature will be. Stream elevation, positive weighting to it. So the higher the stream is, the warmer your temperatures are in the Keynes. So that's the inverse of what we typically think. But look, so we have high stream elevation, which co-occurs with upland wetlands, so there's obviously a feedback going on there. When we put in the high resolution model, we have less variability explained. So our question was, all right, so we put in the LiDAR data and we use the thermal infrared imagery, we're explaining less variability. So we're actually losing power in these models by including more high resolution data. But again, the same thing, you're seeing that the same variables start to pop up. Now we have precipitation between October and July, negative correlation. That's got to do with loading the landscape with water, essentially. So the take-home point here is that the fine resolution model is losing power. Right? So we're putting literally the highest resolution data we have, and we're losing explanatory power. So what would be going on in the Keynes? So here we have the Keynes upland. There's the wetlands here in the black. And if we just focus in on this area here, here's what it looks like. All right, there's your upland wetland complex, right? River's flowing through it, she's flowing down that way. Look at the thermal infrared imagery. It's warm. There's no groundwater inputs there. All right? So this is kind of what the model is pointing towards, all right? So there's no groundwater inputs along this stretch of water here. However, you go downstream to this area, which is being essentially cut by glacial meltwater into the bedrock, and we know that it's sandstone. So we have slopes here that are about 75-degree valley wall slopes. So these are super steep. And what happens when we hang our thermal infrared imagery on it is, well, look, 13.5 degrees coming out of this area here, 14.3, 14.4. So we can start to see that there's groundwater inputs coming from these steeply incised areas. And if we have the upland wetlands, we start to get warm temperatures. So what's going on there is the geology is regulating the stream temperature. And we also, last year, we put, this is Eastern River actually, it gets colder as you go downstream. We put air temperature loggers in the Keynes, and even for the main stem, there was still a buffer from the groundwater in the main stem, even due to solar radiation loading. So that's something that we don't typically think about with rivers. Okay, North Pole streams, a different beast. Again, the A-spatial model is outperforming these spatial statistical models. This, we did not expect this to happen, but what it's interesting here is that we have different covariates explaining the variability. So we have different descriptors that describe the stream temperature. So we have a deep water clastic bedrock, which appears in both models, a negative weighting for it. So basically this is saying where you have a deep water clastic deposit that we have colder temperatures. So deep water clastic here is just sedimentary stuff. Felsic granite rock, so it's impermeable, positive weighting to it. We have average minimum air temperature in July. As that increases, your stream temperature increases. That kind of makes sense. With valley depth here, which is basically a proxy for our valley slope, as that increases here, it's got a positive weighting. As you have deeper incised valleys, you have warmer stream temperatures. So that's the opposite of the Keynes River, right? So how do you manage that? And again, you see the same pattern here. We increase the resolution of the data, and our R squared starts to drop out. Again, you can talk to me about the AICs all you want, and it's just penalizing because there's only one covariant here. Right? So what this is showing is there's something else going on in the landscape that the surface doesn't account for. And you can look at the North Pole stream, and you go back to this map again. So there's your bedrock geology, your superficial or your slope map. So this is basically a slope map of the surface. First, we're going to look at this little quadrant here, and this is in that deep water clastic, so 488 million-year-old bedrock. We have a lake. You can see the groundwater inputs coming in here in the purple. That lake is 17.5 degrees, right? On the day that we flew the thermal infrared, it was 31 degrees Celsius. So there's an offset of 14 degrees between the lake. So that's not a lake that's influenced very much by air temperature. This is a groundwater lake. But what we see here is we have this diffusion, so we have a bunch of groundwater coming in from here, and it drops the temperature by 4 degrees over about an hour and a half. And if you get a closer look at it, we can see again here at a finer resolution, we have the lake, 17.5 degrees Celsius, and then we have these inputs coming in, 10.9 degrees, 8.7 degrees Celsius. So that's coming directly from the bedrock. You go downstream further, so this is where our granite deposit is here, impermeable, remember? We have a really steep channel here. So this valley depth is 19.7 meters there. That's pretty steep. So going back to our model, it said as you increase your valley depth, you have an increase in stream temperature. Here's the thermal infrared imagery, low groundwater inputs there. All right. So again, even within this watershed, Here, if you incise channels, you're going to have cold water. But you come downstream into even here, you're going to have a very different mechanical processes that are going to affect your temperature. So, just a quick recap with the coarse model. So that's with the SRTM data and the hydrographic networks that are from Canada. We have a higher R squared. But the problem with this is that it accounts for less potential refusion. And there's a paper Nathan Wilbur is about to submit, and he was finding that there were seeps in the Keynes that were picking up with the LiDAR that are actually really important for cold water refuge for salmon and trout. So these are like areas that could be, I don't know, the size of the table there, and there could be tens of fish hanging out there. But when we have a fine resolution model, we get a lower R squared, but we account for less of these potential refugia. And the spatial statistical model in this case, and it didn't work. So this, they use this model out in the western out in Washington and Idaho and all these other places. They're getting like really high values, and they're explaining a bunch. But they're using point or temperature loggers that have a much coarser resolution, and all of the geology there is typically mountainous. So it's not the same. New Brunswick is a really ancient landscape. Stuff has been weathered to crap here, and waters flow through the landscape very differently. So why does the spatial statistical model not work? I would argue, and I'm a fool, so I don't know if I'm even right, but we're looking at surface spatial correlation here with this LiDAR, okay? We're looking at the surface, but really what we're finding is it's what's beneath the ground that's really influencing stream temperature. So if we start to build management plans or try to have an understanding about how climate will change, or these rivers are going to change with climate, I would argue that we should be looking towards what's going on underneath the ground, underneath our feet. So with that, we've built a couple of conceptual models that can speak to, okay, if we have an increase in climate, or increase in air temperature, or decrease in drought, which areas might be the best to protect, or which areas might be less influenced by climate change. And our first conceptual model is this of an upland wetland. So this is the low thermal resilience. This would be like the uplands and the Keynes. Here we've got solar radiation exposure, we've got some wetland vegetation, and we've got heat gains from solar radiation and air temperature. All right? We have this impermeable material here, and it could be a clay or whatever, but it's what gives rise to this wetland. These arrows here are groundwater flow paths. So basically, the groundwater comes up here and it tries to intercept or feed this wetland, but the clay layer won't allow the water to penetrate through it, so it comes back down again. And this instance here might be a recharge wetland. So the wetlands in the Keynes, because the rock underneath it is fractured, there's your fractures here and your faults, the wetland actually could be potentially feeding that local, or that bigger sandstone aquifer. So this is why we're seeing that the air temperature has a low thermal resilience, and this is going to be really a victim, if you want to say that, of climate change. So these areas here are going to get warm. As they get warm, the streams are going to get warm. So how do we manage that? I don't know. Age of water is important. And people are talking about pumping out aquifers or whatever. This is where it comes into account. This is young water. Water near the surface is young. And when I'm saying young, it could be a week old, it could be a few years old. But the deeper we go down, the older the water gets, because it takes longer for the water to move through this material, right? So in theory, if you pumped out one of these, and it was old water, and I'm talking about water that could be 1,000 years old, 10,000 years old. There's a brewery in Bavaria, they get their water from a well, and they went away and aged it, and the water was 22,000 years old. Like that's friggin' old, and if you deplete that aquifer, that's not coming back. That's done. It's also pretty cool beer. So, talking about thermal resilience, this is really what's going to underpin that thermal resilience. However, you might have an area where you have an incised channel and permeable bedrock. And this might be an area where you have high thermal resilience. So here we have our shallow deposit here. We've got our groundwater flow paths. But we can see that this area is going to feed into the aquifer. And this is conceptual, right? You can change the geometry as much as you want. But basically, you have water flowing in here, and at some point it goes from feeding to discharging. So this would be an incised valley like we're seeing in the Keynes River. Here, you've cool air temperature. Colder things are more dense than warm things, so you've got this nice cold water, or cold air mat sitting here. You've got deflection of incoming solar radiation, and you have this cold water feeding into here. That's why you have the cold water. All right. So this would be more thermally resilient. Again, area here, you might harvest this, but does that harvest do anything to this groundwater? If it's really old groundwater, it probably doesn't. Because that groundwater, again, could be 10, 20, it could be 1,000 years old. We don't know. We don't know how old the water is in New Brunswick. So these are the kind of dimensions you've got to start thinking. And then the inverse of that would be the lower part of the North Pole stream. So this would be an impermeable bedrock. So let's say, for instance, it's granite. And you can see here that the groundwater flow lines are a lot thinner. The fractures are less. So basically, there's going to be less water stored in this rock than there will be in the other stuff. So maybe if I harvest here, most of the water is coming from a shallow aquifer, and that's going to be more susceptible to climate warming. So maybe we have a different landscape angle or landscape management angle here. So we can see water's closer to the top, it's got a lower thermal resilience. Water here is going to be quite young. In contrast to this, I mean, there could be still cold water coming from here, and in the mountain ranges you see these faults or whatever. But for the most part, it might be discrete inputs, so an input like a seep or whatever, rather than the diffusive input that we see from the, and diffuse just means that it's coming from all the bedrock, like we see in the North Pole stream. Okay, I'll shut up now. So we'll take one take-home message here, and again, like, I'm not a biologist, but hydrologists is the same thing. We've got to really start thinking about the geological environment in which our topic or our species